Okay. Hey guys. Yeah, I got it. Alright, hey Mr. Sue. This is my video for Unit 3, and I'm just gonna jump right into it. Let's go. Right. So we're gonna start off by doing imaginary numbers. I found the book that you use, Mr. Suhu, and it's really helpful. My friend from South uses it anyways. I found the definition for imaginary number. It's the square root of a negative number written in the form b times I, where b is a real number and I is an imaginary unit, radical -1, also called a pure imaginary number. So here are some examples for multiplying, subtracting, and adding through imaginary numbers. This one, we got 2x to the squared minus 11 equals -47. We're going to use easy little algebra doohickeys, and we're going to take the 11 and add it to -47, but it's pretty much like subtracting 11 from a positive 47. We get 36, and we do our division with 2x squared. So 2 divided by 36 first is 18, then we square 18. I used a calculator, I got 4.24. Now this one is a simplification process. What we got one parenthesis set with 9 minus 2i, another parenthesis set -4 plus 7i. What I did at least, is I used the distributive property where I multiplied 9 to -4 and 9 to 7i into the same thing with 2i to -4 and positive 7i. I got 36 plus 63i plus 8i minus 14i squared, because we multiplied an I times an I, so we have 2. And that's my simplest answer. Alright, so now one way that we can use imaginary numbers in real life. America, apparently, in 2012, is calling for a lot of engineers, especially electrical engineers. That's why most of my friends are trying to major in engineering. And what I found was engineers use imaginary numbers in different equations, which relates to a differential equation. Like what I read, it said it relates to functions to growth rates. So it's one of the major formulas that you got to know when you are going to be an engineer. That's why engineers use so much math, and they pay a lot of money. So I guess imaginary numbers get you bank, bro. For this problem, we're going to be finding out the max height and the distance of, I'm going to say, a ball being thrown in the air. So here's our equation. We're going to put that into our y equals right there. Take a look at it. Alright, you got it. Now what we're going to do, we're going to graph it. This is what it looks like. This is what it looks like when I draw it. You can see the difference. Well, it's the same thing, but it's just really bad drawing. Here are my windows. X minimum is -10, then +10 for the max. As y, it's going to be, if that's supposed to be 200, but I changed it, I guess. Makes it easier. Then we got 204.5. Alright, so let's go to the graph. And what we're going to do, we're going to hit second, trace. Bam. Where are we going to go? We're going to do 0. Here we go. So we're going to go all the way to this side. Press enter. Once more. Bam, there we go. You gotta follow the arrows over there. We'll show it right around here somewhere. So here's my X on one side. As you can see right around here, I minimized it to -0.4. Focus. Whatever, you get the picture. Alright. I did the same thing over here. I got 6.04. Now, then you have to find the vertex, and the max height I got was 148, and here's my answer. Yep. So for this problem, we're going to be finding what point on the parabola is greater than 10.5 feet. The parabola is going to be representing a bridge, And that bridge, we're going to see how well a boat can fit under it. Here's our equation. Y equals negative 0.0625 x squared plus 1.25 x plus 5.75. I have it written down right here. And what I have down is that x is supposed to be greater than 10.5. Therefore, we replace 10.5 with, replace y with 10.5. Then we subtract it from itself, cancel that out, and then we subtract 10.5 from 5.75. This is the equation I got where 0 is less than the equation. From there, I got this. 5.1 feet is less than x, which is less than 14.9 feet. Here we go. Alright, that's the end of our video. Let's say bye, guys. Say bye, cat. Say bye.